Okay, hello everyone. Welcome to the Geodesy lecture series. So today, we are very glad to have Kristel Chanard to give a lecture. Kristel did her PhD in France from Normal Superior in Paris. So I'm trying to pronounce France, but I'm not sure it's correct. Hopefully it's correct. And after her PhD, she did her a postdoc from Switzerland, from a University of Lausanne. And now she's a research scientist in IGN in Paris, France. Kristel research interest is in analyzing geodetic observation, including GRIS, GPS, to study the rheology of asthenosphere, lithosphere, and particularly focus on the change of hydrological cycle and their impact on solid Earth. So welcome, Kristel.
Thank you, and thank you for the invitation. It's great to be able to share a bit of what we've been doing recently with you. So today I'll talk about the geodetic signature of continental hydrology. And this work, I'll be presenting this work, but it has largely benefited from students I've been working with. So Louis-Marie Goer, Stacy La Rochelle, Pauline was a former student, and Nelly was an undergrad student now. And from, of course, a lot of discussions with colleagues. So let's take a step back to what deforms the Earth. So we know that the Earth deforms under various internal and external processes, and that by measuring the variations in the Earth's shape, gravity field, and rotation, we can have real valuable information on the physical processes that are deforming the Earth. So this can include earthquakes, but also external forcing, such as astronomical forces, for example. But today, what I would like to talk about is the Earth deforming under climate forcing. Indeed, the solid Earth responds to shifting in hydrological, atmospherical, and oceanic mass. This can tell us things about two different things. First, the climate forcing itself at a range of spatial and temporal scales, looking at the atmosphere, high frequency content in the atmosphere, continental hydrology, or even glacial isostatic adjustment, but also on the Earth's mechanical processes through the deformation mechanisms, whether it's elastic or viscoelastic deformation, or even poroelastic deformation. And one thing I have been trying to do over the past few years is to try to use geodesy as a sensor for climate. Basically, with the emerging spatial geodetic techniques that we have and continuous improvement in data accuracy and resolution, we have an opportunity to monitor two things. The first one is the evolution of the hydrological, atmospherical, and oceanic mass itself through, for example, gravity measurements, which would be the first part of my talk. And then the second thing is the Earth's response to changes in surface loading through measurements of deformation. So the main idea behind this talk is to try to answer this question. So what can geodesy reveal about the water cycle? And this comes with scientific challenges. The first one would be what satellite gravity can reveal about the terrestrial water cycle. And the second one I'll try to answer today is what can we learn on the terrestrial water cycle from looking at the Earth's deformation field in a specific context that I will explain later. Of course, this comes also with quite a lot of technological challenges that I've been trying to answer recently, because when we look at geodetic observations, they actually integrate a lot of different processes over a very wide spatial and temporal scales. So for example, when you're looking at a geodetic time series, you can have a mixture of post-seismic, current ice melting, atmospherical, oceanic loading, and so on. And this can be occurring at a daily temporal scale to decades or centuries, and it could be occurring at the meter scale or even at the global scale. So I guess the technological challenges that we need to face are how to improve the data accuracy and resolution that we have, and how to identify and efficiently separate hydrological processes from other processes in the geodetic time series. So here is the outline of the talk. So I'll first start to tell you a bit about what we've been doing with the GRACE data in trying to measure hydrological loading from satellite gravity. And then in the second part, I'll look at seasonal deformation of the Earth under hydrological loading in a regional example. So first, the first part would be divided in two. I'll try to show you how we try to come up with methods to hunt small wavelength signals in the satellite gravity measurements. And the second one, the second part would be trying to validate those methods against independent observations. So if we look at so what we've been doing is using the GRACE and GRACE Folow-On missions, so gravity and recovery climate experiments, which has a very simple principle because it's just two satellites in a low near circular, near polar orbit that follow each other at a distance along track that is roughly of about 220 kilometers. And what we measure precisely with those satellites is the distance between the two satellites. And this is done using the K-band microwave ranging, or even now, more recently, the laser ranging interferometry for the GRACE Folow-On mission. So what happens is that when the leading satellite is going to fly over a mass anomaly, such as an ice sheet, for example, it's going to be pulled towards the mass, and its orbit will be perturbated. And then the second one will fly over at its turn, and its orbit will be consequently perturbated. By measuring the intra-satellite distance very precisely, we can actually go back to the spatial and temporal variations of the Earth's gravity field that is mapped by GRACE and its Folow-On mission. So we've had decades now of measurements from February 2002 to September 2017 for GRACE, and GRACE Folow-On that has been in orbit since May 2018. So what's really interesting in measuring the spatial and temporal variations of the Earth's gravity field is that it gives us an access to the redistribution of continental hydrology, atmospherical and non-tidal oceanic mass with a resolution of a few 100 kilometers and a temporal resolution of a month. But it's not actually an easy measure. First, we have a lot of observational gaps because sometimes during the mission, the data is just too noisy. For example, this is what you see occurring here in the data availability figure that I have here. It's what you see occurring towards the end of the GRACE mission. But we also have a large 11-month data gaps between missions that is a bit, and that makes the long-term signal analysis quite difficult to perform. So that's the first problem. But the main problem in the GRACE data is the high noise level that shows up as north-south stripes. Here is a figure of the level 2 GRACE Folow-On data for, I think, July 2019, and it's a mean, an average of 4 different monthly solutions provided by 4 different processing centers. What you see once we have removed the static gravity field of the Earth is that if we express the gravity field into equivalent water height here, so it means that it's the equivalent water height that is required to explain the gravity anomaly that we measure, you can see that what we see mostly at first are north-south stripes. And those are occurring because of the orbital geometry of the missions that bear a high sensitivity in the north-south track direction. And consequently, any type of instrumental or processing errors or any shortcomings in the gravity field correction models that we use, for example, for the Earth tides, will translate into north-south striping artifact. So over the past, I think, 2 talks during this this series of talks, we've seen different types of GRACE solutions, but I kind of like to show that first what we see and need to handle is noise. So, of course, to try to come up with ways to filter this noise, there have been over the past decades a lot of different approaches that have been proposed. And the first category is the spherical harmonics approach, plus a type of filtering or constraints. So what this means is that we are going to map the intra-satellite measurements of changes in distance into spherical harmonics basis functions that are defined on the surface of a sphere and that are characterized here with a degree L and an order M that will give us an idea of the shape of and the wavelengths of the function that we're using. And this, so when we map the GRACE measurements onto the spherical harmonic domain, then we need to filter it to remove the north-south stripes. And we can do it through a Gaussian filter, through different types of order degree dependent filter, and through the widely used decorrelation DDK filter, which is, I think, the most used version of the data. And this is all filtering in the spatial domain, and there have been a few attempts at filtering in the spatial temporal domain with principal component analysis or a multi-channel singular spectrum analysis, and I will get back to that a bit later. Another type of filtering method, or not even filtering, but different types of basis function that we want to use to map the GRACE row observations, is to try to do mass concentration blocks. So those are quite useful because it's easier to implement an a priori constraint on the signal that we want to find. And this helps a lot to filter the noise from the observation. So we can use, for example, hydrological models as an input, a priori input into the processing, or even just a land ocean mask to prevent problems in coastal areas. In theory, this is more rigorous than using spherical harmonic decomposition and an empirical post-processing filtering, but it's strongly dependent on the a priori signal distribution, and I'll try to show you how a bit later. All right, so what we've done is start from the decorrelation filter, the DDK filter, because this is the one, I guess, that has a less a priori on the structure of the signal and performs quite well. In fact, DDK is actually a series of filters with different wavelengths of filtering. So you can go from DDK1 to DDK8, and the 8 will be the less filter. So here you have an example for a mean of the 4 processing center from CSR, GFZ, GRATS, and JPL. And it's the on the left, you have, the filter, the effect of the filter DDK5, which has a wavelength of about 370 kilometers. On the right, you have a filter that will retain smaller wavelengths of signals because the wavelength is about 290 kilometers, but you can see, you have still a lot of stripes remaining in the map. So there is really a compromise to make between the degree of filtering that we want and the wavelengths of the signals that we want to retrieve. So basically, always go back and forth between filtering the north-south stripes and retaining smaller wavelength signals and better spatial resolution. And in fact, you can look at it in the spherical harmonic domain. And here you have intensity spectrum as a function of the order and the degree of the spherical harmonic decomposition. And you can see the impact of filtering with DDK5. So basically, if you have a red color, you are leaving the signal and not filtering it. If you have a blue color, you're filtering the signal. And what's interesting here is that if you look at the difference on the right between the DDK7 and DDK5 filters, then you can see that you're filtering with DDK5 a lot of a signal that might actually be real signal, but that you're losing during the filtering. So our objectives were to try to come up with filtering methods for the north-south striping effect and fill the observational gaps that I talked about earlier. And doing so, we want to increase the spatial resolution of the GRACE and GRACE Folow-On data for even more geophysical applications. That's what GRACE has been making possible in the past decades. And for this, we want to start from a lower level decorrelation filter, which is the DDK7, instead of the commonly used DDK5. So we retain smaller wavelength signals and the amplitude of the signals is better resolved. And then we want to develop data adaptative methods with no a priori information, so we can remove the remaining stripes. And to do it, we actually, this is the work, I'm presenting this, but this is a work that has been largely done with my former PhD student, Pauline Prévost, and my current PhD student, Louis-Marie Goer. What we do is that we use the multi-channel singular spectrum analysis. So this is a mathematical method that is going to adapt to the data, and it's multivariate and non-parametric. So what we do is that we try to exploit the spatial and temporal correlation in the GRACE time series with no a priori information on the signal or the noise structure, and we try to remove part of the noise. As a very brief description of the method, what we do is that when we take a time series of the GRACE data at one location in latitude and longitude, in equivalent water height, for example, we want to map this one dimensional time series into a multi-dimensional series of its copied, delayed by a sliding window of length m here, to form a trajectory matrix. When we do this, we want actually to build a multi-channel trajectory matrix of all the time series and their lag copies to try to compute a covariance matrix between all time series and their lag copies. This is done so we can then perform an eigenanalysis and find eigenvalues and eigenvectors to try to project our data into an empirical orthogonal function basis. So this is good because we can then try to compute the reconstructed time series, or at least a portion of it, by choosing the first end components of the signal that we want that we think explain the most variance of the signal. And this is very helpful because it's going to be it's going to help us filter the data. So I tried to make this is all quite technical, so I tried to make a very easy analogy attempt with the Fourier analysis that I think everybody will be familiar with. So basically, in the Fourier analysis, you have a basis function of sine and cosine that you want to use to explain your signal. And here with the M-SSA, we have a basis function that actually has a spatial and temporal component. In the Fourier analysis, you use fixed sinusoidal functions. Here, the functions will adapt to the type of data that we have. And finally, in the Fourier analysis, you have time and space. You are independent in time and space, so you keep the same frequencies and so on. And with the M-SSA, you actually have a spatial temporal principal components in your decomposition. So we use the M-SSA in two steps. The first one is to try to fill the gaps in our observations, in our GRACE observations. And to do so, we perform gap filling using the spatial and temporal information contained in the GRACE and GRACE Folow-On solutions that are processed by 4 different centers, so still CSR, GFZ, GRATS, and JPL. So the blue colors here on the figure on the right, which is a figure of the equivalent water height time series in a point located in the Caspian Sea. So the blue colors are the missing observational gaps, and the one in 2008 is actually a synthetic test. So we just removed 1 year to see whether we could reconstruct or fill the gap and be close or not to the actual data. So what we do is that we do first, and this is the, sorry, I can see my mouse, so I'm not sure if you can see it. But so what we do is in the panel A on the top is that we first do a linear interpolation in the observational gap. Then we remove outliers based on an average, an M-SSA average of all processing centers. This is actually useful in some places where we have large outliers. And then we perform an M-SSA by iteration, and this is panel C here. So you have iterations until you can reconstruct the original, reconstruct the signal. And we perform this by iteration in order to fill the time series and have an evenly sampled time series at the end, and this is panel D. So you can see that for the Caspian Sea, in the synthetic test that we did by removing the year 2008, we can fill the gap with something that is quite close to the data, the original data, which is in gray, and the final reconstruction of the time series is in red. I mentioned that we remove some outliers, and this is quite important in different places, where mostly when the signal is not very big, you have large outliers, and those are the dates that are marked in orange here. And we try to remove them to try to even have a better solution. The second step using the M-SSA is actually the one that is going to be very efficient for removing the stripes. And it's fairly simple. Our assumption here, if we have, for example, the map for July 2019 here, is that if we take a point in the center of the Caspian Sea, then if we take its neighbors going along its latitude, then we will have an alternating stripes, so the blue and red colors here. And so if we perform an M-SSA on this, it's going to show as an uncorrelated signal. And so it will not show as the first part of the signal. So what we do is that we take each point of the globe and we perform the M-SSA with its neighbors. And on the right, you have the results for the Caspian Sea. So on top, you have the initial time series that we started with, which is in blue, and then the final reconstruction, which is in red. And the final reconstruction is actually the sum of the different components that we have, that you have at the bottom here. And so you can see that some of the components have a strong seasonal signal, some of the components are mostly linear and show the long-term mass loss in the Caspian Sea. And we picked the first 8 components as by just looking at the proportion of the signal that is explained by the components, and this is the graph, the figure at the bottom right. And you can see that this is the amplitude of the signal explained by each component by number, and we stop at 8 because it reconstructs the signal pretty well. And we can do it for all the degrees on a global grid. And you can see that in the center of Antarctica, for example, we can reconstruct the signal pretty well, and we remove part of the noise. So the results are here shown as an annual mean annual amplitude for the period 2003 to 2021. And on the top left, you can see this annual amplitude for the DDK5 filter, and on the bottom for the DK7 filtered solution, and on the right for M-SSA solution. What you can see is that we've managed to remove the stripes from the DDK7 filtered map, and we do not have a significant stripes showing on the map. It's quite close actually to the DDK7 to the DDK5 map, but we managed to retain smaller wavelengths in the data. And we can look at it in a linear trend. So it's the gravity anomaly shown between 2003 and 2021. And here you can see as well that from DDK7, we've actually removed part of the signal in mostly stripes in the ocean. And we still have a map that kind of looks like a DDK5 filtered one. And you can see interesting features. So still, for example, you can see the melting in Greenland. You can also see post-glacial rebound signals in North Canada, the Caspian Sea, which is losing mass quite rapidly, but you can also see, for example, Victoria Lake in Africa that is gaining mass. So now that we've done this, we kind of need to validate our method. And the first step that we wanted to make sure of was that in the years that we actually filled the gaps, and especially between the two missions, we are not increasing noise in the data. So this, we've done it by looking at the SLR data, so for only low spherical harmonics degrees, and this is what is shown here. As a function of time, and on the right you have the annual sum of root mean square for the signal. So basically we're comparing our spherical harmonics, low degree spherical harmonics that we retrieve from GRACE with SLR independent estimates. And what you can see is that when we rebuild the data or fill the gaps in the data, so those are the blue marks, then we don't seem to be increasing noise in the data. Another thing that we can look at, and that we were actually quite happy about, was to look at the mean RMS in the oceans. And so on the left, you have, as a function of the year and the months, you have the RMS in the oceans for solution, M-SSA plus DDK7. And then we compared it with different solutions. So for example, DDK5, middle top, which is here for a mean of 4 different solutions. You can see that we have a higher noise level in the oceans. We compared it also with an independent solution, which is doing a kind of an average of solutions, but at the observation level. So it's the COSG solution here on the top right. And you can see that it's also quite noisy in the ocean. And finally, we compared it with a mass count solution. And here we're showing the mass count for the CSR mass count solution in the ocean. And you can see that we actually have reached with our method something that has a noise level in the ocean quite similar to the mass count solutions, but with no a priori on where the signal should be. And this is quite important because when we do regional hydrological mass balance, and this work has been done once again by Louis-Marie Goer and an undergrad student, Nelly Wang-Moussissa. So when we try to do some regional hydrological model, and here I'm showing an example of the method for the Lake Victoria in Africa. And so on the left, panel 1, you have the GRACE and GRACE Folow-On linear trend in the region that we get from our GRACE solution. And you can see that Lake Victoria has a strong positive signal in that period. And then some other lakes around may have negative signals, but Lake Victoria is actually gaining mass. When we want to do regional hydrological mass balance, we kind of have to make sure, if we want to look at Lake Victoria, we want to find the signal in the GRACE data that is actually coming from this lake. So what we do is, this is in panel 2, is that we take the shape of the lake that we are interested in, and we filter it by the same filters that we applied to the GRACE data. And this is what you have in the middle panel at the bottom. So when we do this, you can see that the signal that is actually coming from the lake is spread out all around the lake because of the GRACE resolution and filtering. And it actually has artifacts of using spherical harmonics. So it's red around the lake and then has some negative values around it. So what we do to try to understand in the GRACE map on the left what's coming from the Lake Victoria alone is that we map for each time step, we map this filtered shorelines of the lake with the GRACE data. And this is what you have on the top of the third panel here. We just look for a correlation between the GRACE map and the shape of the lake filtered by the same filters as the GRACE data. And when we do it, we can actually, and this is what is in the bottom of panel 3, sorry, you can see my mouse. You can see that we have retrieved the amplitude in the GRACE data that may be coming from the lake. And you can see that we have a 40 millimeter for this date, actually, for January 2001, we have a 40 millimeter signal that is coming from the lake. So this is important because then we can perform a regional mass balance and compare it with independent data. And in the case of Lake Victoria, we can compare altimetry, elevation variation for Lake Victoria with the GRACE different GRACE solutions. And you can see that all GRACE solutions tend to fairly well explain what the altimetry is seeing, and we can see some differences that may be attributed to several things. First of all, errors in the GRACE data, of course, and then surrounding lakes that we may have missed and will add to what we do later. And then, of course, groundwater. And actually, if we come up with a method that is efficient enough to retrieve mass balance from lakes in a region from the GRACE data, we can actually just look at the differences between GRACE and altimetry, and this should give us an idea of the groundwater variations. So for Lake Victoria, you can see that we have something that fairly well fits the altimetry data, but actually for all GRACE solutions. But now, if we look at different places, so particularly we've been interested in looking at large dams that have been put into water, that have received water recently over the GRACE period. Why? It's because usually the mass count solutions in those places are quite regularized and there is no a priori on the signal. Because we don't know when the lake is going to be filled. And what you can see here for the Bogushani Dam in Siberia is that we retrieve a strong signal starting in 2012 when the lake started to be filled, and we retrieve the volume variation that is very close to the maximum volume of the dam. So this is the blue solution, and you also have two different mass count solutions which are in red and green, and you can see that they don't retrieve this signal because they are strongly dependent on the a priori signal distribution that is used in the processing. This is the same for the Bakun Dam here at the bottom in Malaysia, which started to be filled in 2011, which we see in the spherical harmonic solution, and has a maximum capacity of about 45 kilometer cube, and this is kind of almost what we find. And of course, I think this validates the method for smaller wavelength signals, and we can start to wonder what else we can do at the regional scale. And in particular, you can see that in this GRACE solution that we have now with the M-SSA, you can start seeing some interesting signals, for example, in South Georgia or even in the Kerguelens, that may actually be the signal of the melting glaciers there. And that could not be seen in other types of GRACE solutions. All right, so for the first part, I hope that I've showed you that the GRACE and GRACE Folow-On data can actually reveal smaller scale signals and larger amplitude signals when providing that they are that we use improved filtering methods, and that the comparison with independent data is actually essential to try to validate mass balance using GRACE and assess errors, or even look at different types of contribution to the GRACE data, for example, groundwater or surface water variation. So what's next on this part? We will be releasing this solution for different applications, and we'll try to come up with a user-friendly tool to try to provide a method for estimating mass balance, regional mass balance in targeted areas. And of course, we'll investigate ice mass balance in glacial regions that were masked by other types of processing. All right, so I will now move on to another project that we've been working on, and it's looking at how the Earth deforms under hydrological loading that we can get from the GRACE data, for example, and particularly focusing here on the seasonal deformation. So this work has been largely done by Stacy La Rochelle, I'm sure is connected now, and we've been looking at different types of deformation induced by hydrology. So for example, if we look at aquifer regions, we will have different types of deformation associated with changes in surface and groundwater. So if we're looking at GPS derived deformation, displacement in this kind of region, we'll have an effect that's panel A on top. We'll have a combined effect in the deformation coming from surface water and groundwater. And this can be decomposed in two things. The first one is panel B, the hydrological elastic loading. So basically we have a load on top or inside the Earth that is going to deflect the Earth and also create some horizontal deformation. And then we can have a poroelastic eigenstrain that may be triggered. So basically it's like a sponge. You put water in the system and it creates vertical deformation, and also it can create some horizontal deformation. And we've tried to look at this in a large aquifer system located in central US. So it's called the Ozark Aquifer system. And it's actually a complex aquifer, but it had some advantages, which is that there is very negligible tectonics going there. So most of the deformation that will be seen from using GPS data, for example, will be related to hydrological loading. And then it's a very well instrumented and documented aquifer. Indeed, it's quite well instrumented. On the map, you can see that this aquifer has a lot of GPS stations that are the black triangles, and also a lot of groundwater wells that help us monitor variations in groundwater level. You also have, of course, on the back here, the annual variation in continental hydrology at the large scale that is measured by the GRACE data, and it's in blue colors in the back. What's interesting here is that we've realized, and I think that was not what we were expected at first, we've realized that groundwater level is actually very heterogeneous. So when you look at different groundwater level variations, you can see that for two groundwater wells that are quite close by, so for example, the first one and the second one, you have signals that may be very different. And then if you look at a larger distance, you actually have groundwater levels that quite resemble one another. So we tried to retrieve the aquifer scale signals using the independent component analysis, which is quite somehow similar to the M-SSA. I won't go into details here, but what we are doing is to try to decompose the data set into independent sources of deformation of groundwater level here. And if we do this, we have on the panel A, top left, the groundwater level, the temporal functions of the groundwater level variations. And we retained here 3 different ones, and which is each temporal function, you have a map of the amplitude of the signal associated with this temporal function. So for example, V1, the top one, has a strong seasonal signal and has a strong amplitude that is shown in the middle of the aquifer here with groundwater variations that can reach 30 meters at the annual timescale. We can do the same thing, the ICA analysis on different types of data sets. So we've done it on the groundwater, and that's V1 that is on top in blue. And then we've done it on a GRACE-derived model. So we use the GRACE data, we load the Earth, and we compute deformation at each GPS site. And this is what we get, which is quite similar to the groundwater function. And then we've done it for the GPS data as well. And you can see on the bottom that all the temporal functions correlate very well. And then we've looked at amplitude of the GPS observations compared to the GRACE-derived model. And when we do this, when we've done this, we've realized that there was an anomaly in this region where where the vertical deformation here, annual deformation, measured by the GRACE data was actually larger than the observations. And this triggered our attention because usually at the global scale, it's the opposite. So we actually made the assumption that we were seeing here some poroelastic deformation on top of the elastic deformation. So what we did is that we used our temporal functions. So we corrected the GRACE. The GPS data from the GRACE-derived elastic loading to try to extract what was related to poroelastic deformation due to the aquifer. And then we projected those residuals onto the groundwater temporal evolution to try to retrieve what was related to variations in groundwater in the surface deformation. And we extracted the poroelastic vertical and horizontal displacement this way. So what you can see here on the right is that first of all, the black lines plus red lines, so the GRACE model, they fit well for the vertical displacement to some extent, but not exactly. And then when we look at residuals, so it's the black line with the yellow line, then you can see that we still have some remaining signals, and particularly annual signals in the residuals. So what we've done is project those residuals onto the groundwater temporal function, and it's the yellow line. And you can see that for station ZKC1, so the one on panel A, if we look at the vertical component, for example, at the bottom, there is almost no signal in the correlated part of the signal with the groundwater variation. But this station is actually outside of the aquifer. Now, when we look at a station located inside of the aquifer, so the one on the right, you can see that there is a large portion of the remaining deformation that is correlated with the groundwater variations. So we tried to come up with models to explain that, but we realized quickly that the horizontal deformation was very difficult to model. And this is what is shown on the map here on the right. So it's the difference between horizontal measured seasonal displacement in black and our model in red. And we've attributed this to difficulty in not retrieving the local groundwater variations, because those horizontal displacements are quite correlated, are quite sensitive to what's happening just below the station. So one thing that we could do, we did, was to use the parts that we understood better, the vertical poroelastic displacement, to try to retrieve some useful parameters of the aquifer at a regional scale. So we inverted, we estimated the elastic surface parameters as a function of aquifer thickness, mostly porosity and changes in groundwater level, and of course the vertical poroelastic displacement. And this is what is done on the right, and on the bottom right, the Young's modulus, you can see that we can get an idea of this, the surficial aquifer elastic moduli, and they are variable in space. And this is quite interesting to better understand how the aquifer deform at large scale. We found that those geodetically derived Young's modulus were actually smaller than the one constrained from laboratory measurements for the Ozark rocks, and this may actually explain the presence, may be explained by the presence of fracture, or most unlikely, or a little bit unlikelier porosity. Or different deformation mechanisms that are activated. This is quite interesting because it's an intermediate scale a measurement of elastic moduli that can link the laboratory or small scale measurements with larger scales. All right, so take home message on the second part. So I hope I have shown you that aquifer system can deform both elastically and poroelastically, and that it is possible to separate and identify both components using here the ICA and multiple geodetic data sets. The poroelastic deformation can then be used to infer the in situ elastic properties of the subsurface for the aquifer, and at timescales that may actually not reflect the ones that we get from seismically derived measurements. And then what's next on this part, we've realized that we needed high resolution coverage to better understand what was going on in the deformation. So we are trying to run INSAR in the region at the aquifer scale and try to better understand the variations in horizontal and in vertical and horizontal deformation. And we will investigate other types of aquifer, and Stacy has already been started on an aquifer in California. All right, so as a general conclusion, I think that geodetic observations are becoming a useful tool to monitor climatic variations, and that the GRACE and GRACE Folow-On may keep revealing valuable information, providing that we make some improvements in the data processing. And finally, that we can use multi-technique geodetic approach to identify and separate different hydrological contributions in geodetic time series. And on this, I thank you for your attention. I'm happy to answer questions.
Okay, thank you, Kristel. It's a very nice presentation. It's great to see you include a lot of technical details about the GRACE data analysis and how your novel product can help to explain the hydrological loading deformation. So thank you. So now is the Q&A session. So I will unmute our audience. So if you have a question, then you can unmute yourself and ask the question. So, all right. Any questions? Okay, Bill, I see Bill. Go ahead, please.
Yeah, thanks for the great talk. I was wondering about the stripes in the GRACE, and I know they're related to the orbits of the satellite, but I wonder, are they fixed in time, or do they move around over time? Are the stripes the same, and does that affect your filtering strategy?
No, they unfortunately are not steady in time. They move a bit around, and this is probably why our filter is actually performing well, because the DDK filter is fixed, and it has been designed for a particular month. I don't remember, August, sometime in the early years of grace. And so I think part of the reason that our filtering is making an improvement over the DDK filter is that we actually have the temporal part of the signal here.
So Kristel, I also have a question. So like I see over the dam regions, you compare your solution with the other MASCON solution particularly, and I see the big difference. I'm wondering, do you have any other independent data sets to validate your solution? Because the discrepancy is very big.
So I think you're mentioning this one maybe. So it's actually a bit complicated. This is something I've been trying to think about for quite a while. Validating the grace measurement is a bit of a headache because we have no comparable measurements that could provide some kind of regional estimate. So for example, even when we are trying to look at comparison of grace with altimetry data over lakes, so we've come up with a method to try to extract only what was coming from the lake in the grace data, but sometimes we may have groundwater signals that are polluting the grace signal, and the comparison will be difficult to make. What we've been trying to do is look at places that are quite arid places, isolated lakes. So everything that is in the grace data in that region is actually coming from the lake. This is the best we can do, I think. And so far, I think this is what people have been trying to do. It's very difficult to come up with a good way to validate the grace measurement.
So I see around the figure on the left, I see the data around 2018. So that looks like your solution really is inconsistent with the others. So.
Yeah, and so for the two lakes, dam lakes, actually I should mention that. So the MASCON solution do not seem to see the contribution of those dams because I think they are in areas where the solution is quite regularized. So basically, there was no other types of signals to expect in the region in the middle of Siberia. So everything that was there was actually put somewhere else in the MASCON solution. So I think this might be an issue that MASCON solution should take into account. It's very hard to have a good a priori of where the signal should be.
So we have Roland.
Yeah, Kristel, that was great. Both parts are really cool results. In the second study, where you're able to separate the elastic from the poroelastic deformation, that's really challenging. And I wonder, is the Ozark Basin also a good place where you could incorporate seismic velocity, ambient noise, tomographic data to independently get at the temporal variations of the aquifer behavior?
Yes. Unfortunately, we've looked for data. So we started to look at the Ozark Aquifer before we realized that we could get the elastic properties. And then when we looked at the availability for data, we couldn't find it. But I've been communicating with Loïc Viens, who is doing a lot of noise correlation and who is going to try to investigate that with us. But yeah, we should have somehow a way to validate the elastic properties that we get. Once again, we are looking at the seasonal scale. So there might be somehow different than the seismic ones, the elastic properties. I don't expect them to be so different, but this is something that we should be looking at. Yeah.
Cool. That'll be interesting to see. Thank you.
Yes, I think there is a question from Michel.
Yes, merci beaucoup pour la présentation brillante. I would like to know, that's a problem I have with my data. When you fill in a gap, I have no problem with the way you try to improve the stripes and the spatial gaps, but in time, when you have, for instance, a long gap between Greece and Greece Folow-On, it looks fair to me to interpolate a trend or maybe seasonal, but aren't you afraid that if you go further, as you do, how can you ensure it's the true world? You may just imagine a climato-sceptic is listening to you. He may tell you are doing fraud. Excuse my tough words, but I'm a little provocative. But I'm curious to hear.
No. It's a great question. Actually, I should have mentioned that. I probably forgot. But one issue with the M-SSA method is that we need to have an evenly spaced time series to perform the analysis. So we must fill the gaps. And we could have done it with just a linear interpolation, but we kind of wanted to push the method a bit further. So what we do is that, I can go back to the slide. We start with the linear interpolation and then we fill the gap, and it's true, it's not a real data. That's why we keep those blue indications there that this is actually not a data that we should be interpreting. But when we use the spatial and temporal correlation from the entire time series, we actually retrieve very well the seasonal part and a bit of its complexity. And then another reason that we are doing this is that sometimes some centers do not have a solution for 1 month because they decided that it was too noisy. So we take the information from another one. So for the long gap, what you're saying is right. For the others, quite often we have some information, some true information. But for the long gap, we were actually quite happy to see, and I can show you, quite happy to see that if we compare, actually this one doesn't work very well, but some others do, but we never interpret the differences between our gap filling and the actual true data, because of course they are not real data.
That's a fair answer. Thank you.
Yeah, you're welcome.
I can see Susan is raising hand. Go ahead, Susan.
Yeah, hi, Kristel. Thank you very much for your talk. I enjoyed very much. My question is also related to these gaps. You somehow nicely show that with your approach, you can fill these gaps. Did you check the opportunity of predictions?
Not yet. This is something that we have planned, but not yet for the gray solution. No.
Yeah, I think it would be interesting.
Sorry.
Would be interesting. Thank you.
Thanks.
So I don't see any other questions coming in Zoom. So if there's no question from our audience, then let's give a final applause to Kristel. And also thank you everyone for attending today's lecture. So our next lecture will be on March 23. Looking forward to see you all next lecture. So I will see you. Bye-bye. Thanks, Kristel. Thanks, everyone.
Bye.